This module will review some of the off-equatorial impacts to the global circulation caused by latent heating in the tropics. In particular, we'll look at the impacts of variability in tropical convection caused by ENSO and the MJO on mid-latitude weather. Again, we'll start by looking at a typical distribution of sea surface temperature, and although this is not a long-term average, it does capture the basic features of the SST distribution during boreal summer. Again, the deepest, most persistent convection in the tropics typically occurs here over the Indo-Pacific warm pool, and variability to this convection has impacts on mid-latitude dynamics far from where the tropical convection occurs, as we'll see shortly. Interannual variability, such as ENSO, modulates the frequency of convection throughout the Pacific. For example, during El Niño, convection, and thus latent heat release in the atmosphere, shifts toward the east in the central or even eastern Pacific. On shorter subseasonal timescales, the MJO also modulates convection, particularly over the maritime continent, Indian Ocean, and West Pacific. The variability in tropical heating causes off-equatorial Rossby wave trains to develop and propagate, which we'll now explore a little. In a simple atmospheric model, an anomaly of diabatic heating can be inserted as an initial condition, and the response can tell us about the Rossby response to this heating. For example, consider the current figure from a 1982 paper. In the upper right of the figure are contours that indicate where latent heating was placed in the model. This is located over Southeast Asia and the West Pacific, north of the equator. And what we're seeing here is in projection with the pole at the center. The heating had a first baroclinic-like vertical structure with maximum heating near 400 millibars. The model also included seasonally appropriate zonal winds as a function of latitude. The steady-state response to that initial forcing is seen here. The approximate location of the initial heating anomaly is depicted by the red X in each panel. And the different panels indicate the perturbation geopotential at different pressure levels. So here's 500, 100, 700, 300 millibars. A couple of things are obvious. First, a wave train develops and appears to propagate over the North Pole and into Europe and even moving into West Africa. So you can see here's the heating, then there is a low geopotential anomaly, a high, a low, a high geopotential anomaly. Second, the structure is similar at all levels, except its magnitude is a bit larger in the upper troposphere. This indicates that the response is approximately barotropic. Interestingly, the response to heating had seasonal dependence in the model. On the left are geopotential anomalies caused by heating at 15 north and 15 south in January, and on the right is the same for July. The geopotential response is maximized for the heating in the same hemisphere during the winter. So if I put the heating at 15 north, I get a northern hemispheric response during January, and in the winter in the southern hemisphere, I get the maximum response when I put the heating at 15 degrees south. Finally, the extratropical response is maximized for off-equatorial tropical heating. Heating at higher subtropical latitudes elicits a more muted response, but near equatorial heating, like this at 5 degrees north, also produces a small extratropical response, largely because the vorticity generation by heating focused near the equator is small. So this heating maximum around 15 degrees north seems to produce the largest response. Practically, this means that disturbances that modulate off-equatorial convection in the tropics can alter mid-latitude geopotential and therefore weather patterns. Variability in monsoonal convection is one example of an off-equatorial tropical source of heating that can modulate extratropical geopotential. The Rossby wave component of the convectively active MJO also elicits off-equatorial latent heating that might occur in this 10 to 15 degree north band or so. ENSO generally modulates heating on larger spatial scales for longer time periods in the MJO and also affects the propagation of Rossby wave trains out of the tropics. By shifting the pattern of geopotential globally, the tropical disturbances can impact weather in the subtropics and extratropics on timescales consistent with the tropical variability. The barotropic Rossby wave train excited by tropical convection can also be represented analytically. The dispersion relationship describing the motion is shown at top with zonal and meridional wave numbers included, as K and L respectively. The M subscripts just indicate that a Mercator projection is used, and so the mean zonal wind and beta are scaled to the new projection. The group velocities in both the zonal and meridional wind direction are shown, and the magnitude of the group velocity for a stationary wave, with omega equals 0, is shown down here at the bottom. This tells us that the group velocity for a stationary wave depends on the sign and the magnitude of the mean zonal wind, which is generally westerly aloft at mid-latitudes. So if we go back up here and look at the zonal wave or group velocity, this means that the energy in the Rossby wave train tends to propagate faster zonally than the phase of the wave and can cause amplification of existing downstream geopotential anomalies. The figure on the right shows how the phase of the wave propagates off the equator and toward the east with the mean flow as we increase in latitude. The position of the anomalous troughs and ridges affect the mean storm tracks at mid-latitudes. The quasi-stationary Rossby response is largely responsible for many of the extratropical teleconnections to tropical heating. Shown here are known climatological relationships between anomalous heating over the Pacific during El Niño and anomalous interannual variability in surface weather conditions in the Pacific and elsewhere. The sign of these changes can be approximately reversed for La Niña conditions. So, during the winter time in El Niño, we might have warm conditions in the Pacific Northwest, warm in northeastern North America, cool and wet in the southeastern U.S., for example, and the opposite of this, roughly speaking, during La Niña. And of course, the expected relationship is seen over the Central East and West Pacific into the maritime continent. During a strong El Niño event, anomalous divergence aloft and deep tropospheric diabatic heating may be found over the Central Pacific or maybe even a little bit further east, such as in this example of the 1986-1987 El Niño. This equatorial anomaly, or near equatorial anomaly, excites a stream function that extends well off the equator, I should say a stream function pattern that extends well off the equator as a wave train that roughly follows the red lines. Correspondingly, we have this in the southern hemisphere as well. But since the response is shown during boreal winter, the signal is stronger in the northern hemisphere than in the southern hemisphere. This tropical heating drives a wave response that causes, just as an example, troughing as far away as the western Atlantic and the southeastern U.S., a bit of ridging here in North Africa, ridge here and anomalous trough there. The extratropical response to tropical heating anomaly can occur in just a couple of weeks, as seen as in this time series map of perturbation stream function for anomalous latent heating in the Central Pacific. So the anomaly would be, the heating anomaly would be somewhere down here, and then after 3, 5, 7, 9, 11, and 13 days, the corresponding anomalous stream function excited by that heating is mapped here. A high amplitude wave train sets up over North America within 2 weeks that is consistent with the El Niño teleconnections observed in the United States, roughly. Ridging over the western part of North America, where you get that warm temperature in the Pacific Northwest, and then troughing in the east. The first signal, however, reaches North America within about a week. It doesn't reach Europe until maybe about 2 weeks or so. The response is essentially of opposite sign during La Niña, which is shown here. The MJO also causes variability in tropical precipitation, although it acts on much shorter timescales than ENSO. Nonetheless, subseasonal variability in the extratropical circulation is seen as a result of modulation and heating over the tropical warm pool associated with the MJO. In this figure, each panel represents a different so-called phase of the MJO, and the colors indicate the anomalies of blocking frequencies over the North Pacific. Blocking refers to the formation of high-amplitude ridges that reduce or eliminate the zonal flow that guides the typical storm track at mid-latitudes. Each panel therefore represents the change in blocking frequency from a long-term mean when convection in the MJO is located in a certain location consistent with the phase listed. So we're working from phase 1 to 2 to 3 to 4 and so on down the figure. For example, if we're looking at phases 3 and 4 in the second row, recall that convection is more active then than normal over the maritime continent. These plots here show that clear subseasonal variability in blocking frequency with statistically significant results hashed. For example, during phase 4, less than normal blocking, which could be also interpreted as more than normal troughing, is seen over the North Pacific. During phase 8, the opposite is true, and more than typical blocking occurs. Anomalous troughing may be seen, for example, over the Northeast and Pacific Northwest, or in nearby oceans when the MJO convection projects onto the first two principal components of subseasonal OLR variability in the tropics, such that the MJO phase is 5. See the module on MJO identification for more information about MJO phases. Similar behavior is seen in the North Atlantic as well. Plotted here are blocking frequencies at 5, 10, and 15 days after phases 3 on the top or 7 on the bottom of the MJO occurred. And again, the color shading is the same as on the previous slide, such that blues indicate less than normal blocking. Generally, anomalous troughing or less than normal blocking is in place 1 to 2 weeks after phase 3, and anomalous blocking is present in the same time period after phase 7. Amplification of the signal is seen between 5 and 15 days after the anomalous heating in the MJO occurs because some time is required for the Rossby wave train to reach the North Atlantic, which explains the delay in the signal arriving and then amplifying. In fact, by the time the MJO is at phase 7 down here, convection is relatively suppressed over the Indo-Pacific, and the blocking signal seen over the Atlantic probably emanated from the convection several days prior when the MJO was at phase 3. This type of delayed response can be seen in Hofmahler-like plots that use MJO phase on the y-axis as a proxy for time increasing going upward, assuming that the MJO phase always progresses forward from 1 to 8 and then back around. We'll see more plots like this in the paper discussion for this topic this week. Shading on this plot represents the anomalous frequency of atmospheric rivers at some time period listed on the x-axis after the phase shown on the y-axis. Plots are shown for the Pacific Northwest, specifically British Columbia, and for California. As an example, the dark green color in the red circle means that more than normal, there's a positive percentage up here, more than normal atmospheric river activity occurs in British Columbia about 14 to 21 days, reading off the x-axis, after the MJO was in phase 2. So when the convection in the MJO is phase 2, kind of eastern Indian Ocean, western maritime continent, or phase 3, then it's sometime later, maybe a couple weeks, maybe 3 weeks, before you get anomalous atmospheric river activity in the West Pacific. So there's a little time delay. As the MJO convection moves eastward and its circulation eventually becomes decoupled from the convection, the leftover already produced Rossby response will continue to propagate so that the anomalous troughing and atmospheric river activity reaches the coast by the time the MJO is in phases 5 or 6 or so. So this plot would tell you that 0 to 2 days after the MJO is in phases 5 or 6, you tend to get anomalous AR activity. Similar behavior is seen in California, although the negative signed response is higher in amplitude in most phases. This may be indicative of MJO-driven subseasonal variability of Santa Ana wind events. Finally, just as a few more examples, the MJO can affect other types of weather events as well, presumably through the extratropical Rossby wave train that anomalous tropical heating excites. This figure was borrowed from a paper that examined subseasonal variability of severe weather over the central United States. Similarly to the last plot, we can see how a lag response exists between severe weather events or their thermodynamic and dynamic indicators and MJO activity. And the dotted squares with the white dots in them indicate statistically significant results. Currently, models do not capture this type of variability very well, and that means that the possibility still remains for gaining more skill at predictability for medium lead times of 2 to 3 weeks.